December 16th, 1944. 05:30 hours. Monschau, Germany. Colonel George Axelson stood in the command post of the 406th Artillery Group, holding a field telephone in one hand and a top-secret directive in the other. Through the static-filled receiver, he could hear the desperation in Captain Robert McClernand's voice. The 38th Cavalry Squadron was dug in around the town, lightly armed reconnaissance troops facing the opening barrage of what would become the Battle of the Bulge. They needed artillery support. They needed it now. Axelson looked down at the wooden crate beside his desk. Inside were shells unlike anything the Wehrmacht had encountered. Each one cost more than a jeep. Each one contained technology so revolutionary that Supreme Commander Eisenhower had personally forbidden their use without his explicit authorization. The fear was simple. If even one shell fell into German hands intact, enemy engineers might reverse engineer the mechanism or develop countermeasures that could neutralize the Allies' most devastating technological advantage. "Colonel, we've got SS infantry moving on our positions in company strength." McClernand's voice cracked slightly. "We need fire support or we're pulling back." Axelson made his decision in the space between heartbeats. The emergency trumped the restrictions. He turned to his fire direction officer, Major Thomas Sherburne. "Load Posit. All batteries. Tell the gun crews this is what we've been saving them for." Posit was the code name, deliberately vague, designed to reveal nothing. Variable time Fuze, the official designation, was equally deceptive. What the crates actually contained were proximity fuses, radio transmitters small enough to fit in the nose of an artillery shell, sophisticated enough to sense when they approached a target, and rugged enough to survive being fired from a cannon at accelerations that would crush a man to paste. The German engineers who would later examine captured examples would declare them physically impossible. Within minutes, the guns of the 406th spoke. Not the usual thunderous barrage, but something that sounded almost identical to the crews. The shells arced through the pre-dawn darkness, their trajectories calculated not for ground impact, but for airburst detonation above German positions. What happened next violated every principle of artillery warfare the Wehrmacht understood. Obergefreiter Hans Müller of the 12th SS Panzer Division had survived 3 years on the Eastern Front. He knew artillery. You heard the whistle. You dove for your foxhole. You pressed yourself against the frozen earth. And you prayed the shell wouldn't land close enough to matter. The log-reinforced bunker he and his squad occupied had weathered Russian artillery for weeks outside Kursk. It would handle American shells. The first rounds didn't land. They exploded 70 feet above the ground, each one transforming into an expanding sphere of death. 3,000 square feet of lethal shrapnel traveling at velocities that made foxholes irrelevant and overhead cover meaningless. The shells Müller expected to hear impact with a muffled crump instead detonated with sharp, vicious cracks directly overhead. "They're using airburst!" someone screamed, but that made no sense. Airburst required perfectly timed fuses, calculated to the second based on range and altitude. In the chaos of combat, in the pre-dawn darkness, with targets barely visible, achieving airburst precision was impossible. Yet shell after shell exploded at exactly the right altitude, each one seeming to know precisely where the ground waited below. Müller pressed harder against the bunker's log wall as shrapnel tore through the roof, through the logs that should have been protection, through the frozen earth itself. The sound was wrong. Artillery shells landed before they exploded. These exploded in mid-air with a synchronization that seemed intelligent, malevolent, impossible. His squad mate, a veteran named Ernst Vogel, was muttering prayers. How are they doing this? How do they know the exact height? The mathematical precision required boggled the mind. Every shell needed individual fuse setting based on trajectory. Every calculation needed to account for barrel wear, propellant temperature, wind conditions. Human beings couldn't achieve this accuracy even with perfect observation and unlimited time. The Americans were doing it blind, in darkness, with every single shell. When the barrage lifted, Muller's squad emerged into the morning light. Of the 43 men who had occupied positions around the bunker, he counted 14 still moving. The rest lay scattered in poses that spoke of death from above, wounds that shouldn't have been possible from artillery that never touched the ground. Captain McClernand, watching through binoculars from the cavalry positions, saw the German attack falter, then dissolve. What the hell was that? His artillery liaison officer, a lieutenant who'd arrived just 2 days earlier, wore an expression somewhere between awe and terror. That, Captain, is why we're going to win this war. The Germans just encountered physics they don't believe exists. What neither the German soldiers nor most American troops understood was that they were witnessing the culmination of a 4-year scientific miracle. A weapon that had consumed $1 billion 1940s dollars, $15 billion in modern terms. A project that had employed more physicists than any other wartime effort except the atomic bomb. A technology so revolutionary that it required inventing entirely new manufacturing techniques, creating components that had never existed, and solving problems that the world's best engineers had declared unsolvable. The story had begun 4 years earlier, in the desperate summer of 1940, when Britain stood alone and American scientists understood that conventional anti-aircraft fire was effectively useless. Dr. Merle Tuve sat in his office at the Carnegie Institution's Department of Terrestrial Magnetism in Washington, studying a problem that had defeated military engineers for decades. Aircraft were too fast, too maneuverable, too small. A 5-inch anti-aircraft shell, traveling at 2,000 feet per second, had to intercept a target moving in 3 dimensions at 400 miles per hour. The mathematical challenge was staggering. A direct hit required predicting not just where the aircraft would be when the shell arrived, but accounting for the shell's trajectory, the aircraft's evasive maneuvers, wind conditions, and a dozen other variables. Timed fuses, set before firing to explode at a specific altitude, were marginally better than contact fuses, but still required almost supernatural prediction. Get the timing wrong by 1/10 of a second, and the shell exploded harmlessly hundreds of feet from its target. The success rate against modern combat aircraft was approximately 3%. What Tuve needed was a fuse that could think, that could sense its target, and detonate at the optimal moment. The concept wasn't new. German engineers had been working on proximity fuses since the early 1930s. British scientists had conducted experiments in 1939. The idea had been proposed, studied, attempted, and abandoned by nearly every major military power. The problems were simply too severe. The fuse needed to be small enough to fit in a shell nose, typically less than 3 inches in diameter. It needed to survive accelerations of 20,000 times the force of gravity when fired. The electronic components had to function reliably after experiencing forces that would pulverize any normal radio equipment. It needed to operate on battery power for the 30 seconds or less between firing and detonation, and it needed to be cheap enough to manufacture by the millions. Every attempt had failed. The British had given up. The Germans, in 1940, had officially terminated their program via Führerbefehl, Hitler's directive that halted all weapons development that couldn't be completed within 6 months. The physics simply didn't work. Fuze, examining the thick book of failures and thin book of possibilities compiled by previous research, decided the thick book was asking the wrong questions. The key wasn't making conventional radio components smaller. It was inventing entirely new components designed specifically for this impossible application. In August 1940, the National Defense Research Committee gave Section T, Fuze's group, a blank check and an impossible deadline. The U.S. Navy needed working proximity fuses for 5-inch anti-aircraft guns, not prototypes, not experimental units, combat-ready fuses capable of mass production. What happened over the next 18 months was less engineering than alchemy. Dr. James Van Allen, who would later discover Earth's radiation belts, worked 16-hour days developing vacuum tubes that could survive being fired from cannons. The standard glass tubes used in radios shattered under forces 1,000 times weaker than artillery acceleration. Van Allen's solution was elegant. Redesign everything. Shorter tubes, thicker glass, novel internal structures. By January 1942, he had created vacuum tubes that laughed at forces that would kill a human being. Lloyd Berkner solved the transmitter problem by separating the circuits, allowing the same antenna to send and receive signals. The principle was simple. Bounce radio waves off the target, measure how long they took to return, detonate when the delay indicated close proximity. The execution required inventing miniaturized components that didn't exist and couldn't be purchased from any manufacturer on Earth. The battery alone was a marvel. It needed to deliver reliable power despite sitting idle for months in storage, activate instantly when fired, operate at temperatures from Arctic cold to tropical heat, and function flawlessly for exactly as long as needed. Too short, and the shell couldn't reach its target. Too long, and you wasted expensive components. By the summer of 1942, Section T had assembled something that shouldn't have been possible. A 5-inch shell nose packed with 130 separate electronic components. 5 vacuum tubes, each one a miniature masterpiece of engineering. A battery smaller than a deck of cards. A radio transmitter, a receiver, amplification circuits, and a detonation mechanism all crammed into a space the size of a coffee can, and designed to survive forces that would liquefy organic tissue. On August 12, 1942, the light cruiser USS Cleveland conducted live fire tests in Chesapeake Bay. The targets were 3 radio-controlled drone aircraft, small and maneuverable, difficult to hit under the best circumstances. The test was scheduled for 2 days. The Navy canceled the second day when gunners destroyed all 3 drones with just 4 shells on the first morning. The drones had been evading frantically. It didn't matter. The shells found them anyway. Production began immediately. But even with 5 major manufacturers and 80 subcontractors, the complexity was staggering. In late 1942, Crosley, RCA, Eastman Kodak, General Electric, and McQueen Norris were producing 500 fuses daily. Each one cost $732, more than most workers earned in 2 months. Each one represented hours of meticulous assembly. With women workers, the men were at war, soldering components under microscopes, testing circuits, calibrating sensitivities. The technology was so sensitive, so revolutionary, that the mere knowledge of its existence could change the war. The Pentagon imposed security more stringent than most atomic bomb facilities. Workers signed secrecy oaths without being told what they were building. Components were manufactured in separate facilities. No single contractor saw the complete design. The code name Variable Time was deliberately misleading, designed to sound like a conventional timed fuse with adjustable settings. And absolutely, under no circumstances, were the fuses to be used where they might fall into enemy hands. Which brought Colonel Axelson back to his decision that December morning. He had violated direct orders. The shells falling on German positions around Monschau contained technology that wasn't supposed to exist. If the Germans recovered even one intact fuse, if their engineers understood what they were facing, the consequences could be catastrophic. But the 38th Cavalry Squadron held their positions. The SS infantry attack shattered against artillery that could see in the dark, that could reach into bunkers, that could kill with shells that never touched the ground. And across the Ardennes, as the Battle of the Bulge exploded into full fury, American artillery commanders faced the same choice Axelson had made. Within 48 hours, Eisenhower himself lifted the ban. 200,000 Posit shells were deployed to the European theater. The Germans were about to discover that the physics they had declared impossible was killing them by the thousands. The transformation from theoretical impossibility to battlefield reality had taken 4 years, $1 billion, and the combined efforts of America's finest scientific minds. What it had produced was a weapon that would make foxholes obsolete, render overhead cover meaningless, and prove that in modern warfare, the side that could make the impossible routine would write the terms of surrender. Obergefreiter Hans Müller, huddled in what remained of his bunker as dawn broke over Monschau, didn't know any of this. He knew only that something had changed, that the Americans had developed artillery that seemed to think, that could find you wherever you hid, that killed with a precision that suggested either perfect observation or actual magic. He would survive the war. In 1947, during a POW debriefing, an American intelligence officer would ask him about the Battle of the Bulge. Müller's response was simple. After the first morning, when those shells started exploding overhead, we knew. Whatever the Americans had invented, we had no answer for it. Our engineers told us it was impossible, but impossible things were killing us anyway. The mathematics of destruction were already written in those radio waves, bouncing off targets at the speed of light, measuring distances with precision that made human calculation irrelevant. The Germans had spent a decade trying to solve the same problem. They had failed because they believed the problem was unsolvable. The Americans had succeeded because they refused to believe in impossible. The problem was deceptively simple to state and murderously complex to solve. Dr. Merle Tuve, sitting in his cluttered office at the Carnegie Institution, had reduced it to a single sentence written on his chalkboard. Make a radio small enough to fit in a shell, tough enough to survive being fired from a gun, and smart enough to know when it's close to an airplane. Each requirement contradicted the others. Radios in 1940 were delicate instruments filled with glass vacuum tubes, housed in wooden cabinets, powered by wall current or bulky batteries. The idea of cramming transmitter, receiver, amplifier, and power source into a 5-inch diameter shell nose was absurd. The notion that these components could survive 20,000 G-forces, accelerations that would turn a human body into liquid, was laughable. But Tuve wasn't laughing. He was looking at casualty projections from Britain, where German bombers were systematically destroying cities, while British anti-aircraft guns fired thousands of rounds to achieve single kills. The mathematics were brutal. A formation of 10 bombers could devastate a city block. Stopping them required hundreds of shells, dozens of gun crews, and extraordinary luck. "Show me the failures," Tuve told his assistant, Richard Roberts, when Section T officially began work in August 1940. Roberts produced a thick binder documenting every attempt to create proximity fuses over the previous 2 decades. acoustic fuses that triggered on engine noise, defeated by wind and their own shell's passage through air, photoelectric cells that sensed light changes, blinded by clouds, useless at night, magnetic fuses, too weak, too unreliable, and radio fuses, the most promising concept, which everyone agreed were theoretically perfect and practically impossible. Tuve read through the failures in silence, then closed the binder. These people were trying to miniaturize existing technology. That's backwards. We're not making radios smaller. We're inventing new radios that happen to be small. The distinction seemed subtle. It would prove revolutionary. The first challenge was the vacuum tube. These glass cylinders were the heart of every radio, amplifying weak signals into usable power. Standard tubes were 3 inches tall, fragile as light bulbs, and required careful handling. Artillery shells experienced forces that made careful handling a distant fantasy. Dr. James Van Allen, a young physicist who would later discover the radiation belts encircling Earth, took on the vacuum tube problem with an approach that seemed almost recklessly simple: make them smaller, stronger, and completely different from anything that had existed before. His laboratory at the Applied Physics Lab, Section T, had moved to Johns Hopkins University in 1942 when the project outgrew Carnegie's facilities, became a workshop of controlled destruction. Van Allen would construct a tube, mount it in a test shell, fire the shell from a gun, and examine the wreckage. Glass shattered. Filaments snapped. Internal elements crushed themselves against tube walls. The forces were simply too extreme. The problem, Van Allen explained to Tuve during one particularly frustrating week, is that we're fighting physics. The tube elements want to move when the shell accelerates, but there's nowhere for them to move. They're already pressed against the glass. Then don't give them room to move, so, Tuve suggested. Make everything so rigid that movement becomes impossible. Van Allen stared at him for a moment, then spent the next 3 days at his workbench. When he emerged, he was holding something that looked less like a vacuum tube and more like a miniature cathedral of glass and metal. The tube was barely an inch tall. The glass walls were 4 times thicker than standard tubes. The internal elements were so tightly constrained that they couldn't vibrate even when shaken violently. They fired it from a test gun. The tube survived. More importantly, it still worked. By January 1942, Van Allen and 2 colleagues held a patent for vacuum tubes capable of surviving artillery launch. The achievement was so significant that the military immediately classified the entire design. Enemy scientists couldn't be allowed to know that such tubes existed. But a rugged tube was only the beginning. The fuse needed a transmitter small enough to fit alongside 4 other tubes, a receiver sensitive enough to detect reflections from small targets, an antenna that could function while spinning at 300 rotations per second, and a battery that could deliver power reliably despite months in storage. Lloyd Berkner solved the transmitter-receiver problem with elegant simplicity. Instead of separate circuits for sending and receiving, he designed a system where a single oscillator did both jobs simultaneously. The circuit transmitted a continuous radio frequency signal. When the shell approached a target, reflected waves interfered with the outgoing signal, creating a distinctive pattern. An amplifier detected this interference, and when it reached a threshold indicating close proximity, a relay closed and detonated the explosive. The physics were straightforward. The engineering was nightmarish. Every component needed to be miniaturized without losing functionality. Wire connections had to survive violent shock. Solder joints couldn't fail under extreme acceleration. The entire assembly had to function reliably at temperatures from -40 to +120 degrees Fahrenheit. Sylvania solved the battery problem by developing a specialized design using magnesium and silver chloride. The battery remained inert during storage, but activated instantly when the shell fired, the acceleration itself triggering a chemical reaction that generated power. It would function reliably for exactly 45 seconds, long enough for any reasonable artillery engagement, short enough to prevent wasting expensive components. Each advance revealed new problems. The antenna needed to transmit and receive while spinning at dizzying speeds. The solution was a simple dipole design that remained effective regardless of orientation. The safety mechanism had to prevent premature detonation. You didn't want shells exploding in the gun barrel, but activate reliably once airborne. The answer was a centrifugal switch that closed only when the shell reached firing rotation speed, combined with a timer that prevented detonation for the first few hundred yards of flight. By mid-1942, Section T had assembled a working prototype. The Mark 32 Fuze, designed for the Navy's 5-inch gun, contained 130 individual components packed into a space 5 inches long and 3 inches in diameter. It weighed just over 2 pounds. The manufacturing cost was horrifying, over $700 per unit when a new car cost $800. Testing revealed both the Fuze's potential and its limitations. In laboratory conditions, prototype Fuze worked beautifully. Fired from guns, they became temperamental. Some failed to activate. Others detonated prematurely. A few exploded on the firing line itself. The problem was consistency. Laboratory conditions were controlled, predictable. Combat was chaos. The solution required inventing quality control processes that didn't exist. Every component needed testing. Every assembly required verification. Crossley Corporation, assigned to mass production, created an assembly line where women workers, men were at war, performed operations under microscopes, testing each connection, calibrating each circuit. The reject rate was astronomical. For every 10 fuses assembled, only 6 passed final testing. But when they worked, they were magic. The live-fire test aboard USS Cleveland in August 1942 proved the concept beyond any doubt. 3 remote-controlled drones, maneuvering evasively over Chesapeake Bay, destroyed by 4 shells. The gunners weren't aiming with supernatural precision. They were simply pointing in the general direction and letting the fuses do the rest. Navy officers watching the test understood immediately that they were witnessing a revolution. Captain Schumacher, director of the Bureau of Ordnance's Research Division, coined the term VT Fuze, variable time, specifically to hide the true nature of the weapon. If enemy intelligence heard about proximity fuses, they might understand what they faced. Variable time sounded like a conventional timed fuse with adjustable settings, nothing revolutionary. The security protocols rivaled the Manhattan Project. Workers signed secrecy oaths under penalty of court-martial. Component manufacturers received no information about how their parts would be used. Assembly workers were told they were building radio equipment for aircraft. The actual circuitry was known only to top-level engineers, and even they didn't see the complete system. Production ramped up with agonizing slowness. 500 fuses daily in late 1942, 5,000 daily by mid-1943, 40,000 daily by late 1944. Each fuse represented hours of skilled labor. Each one cost progressively less as manufacturing improved, from $700 in 1942 to $18 by 1945. But even at peak efficiency, the fuses remained expensive enough that their use was carefully rationed. The first combat deployment came on January 5, 1943, in waters off Guadalcanal. The light cruiser USS Helena faced 4 Japanese Aichi D-3A dive bombers, obsolete aircraft, slow and vulnerable, but still deadly if they reached attack position. Lieutenant Red Cochran, commanding Helena's aft 5-inch battery, had been briefed on the new fuses exactly once, a terse explanation that boiled down to load them, aim in the general direction, and watch what happens. What happened exceeded every expectation. 2 salvos, perhaps a dozen shells, and one of the Japanese bombers simply disintegrated. Not shot down, atomized. The other 3 broke off their attack. Cochran, watching through his fire control station, couldn't process what he'd seen. The bomber had been at least 50 yards from the nearest shell burst. In conventional terms, that was a clean miss. But the proximity fuse had detonated at precisely the right distance, and the bomber had flown directly into an expanding sphere of shrapnel traveling at lethal velocities. The Japanese pilots reported nothing unusual. Their squadron mate had been hit by anti-aircraft fire. That American gunners were suddenly, inexplicably more accurate wasn't worth mentioning. Imperial Japanese Navy intelligence recorded the loss as routine, which was exactly what American commanders wanted. The longer the enemy remained ignorant of the new technology, the more effective it would be. The restriction on using fuses over land remained absolute. At sea, dud shells fell into water thousands of feet deep, safely beyond enemy salvage. Over land, unexploded shells could be recovered, studied, reverse-engineered. The restriction frustrated American artillerymen who understood that proximity fuses would revolutionize ground combat. Anti-personnel effectiveness would increase by orders of magnitude. Foxholes and trenches, the infantrymen's salvation since World War I, would become death traps when shells exploded directly overhead. But the risk of technology transfer was too severe. By mid-1944, the fuses had proven themselves repeatedly in the Pacific. Naval combat reports showed that proximity-fused shells were 3 to 4 times more effective than conventional ammunition. More significantly, they achieved a 51% kill rate while comprising only 25% of ammunition fired. The fuses were outperforming conventional shells 3 to 1 in every measurable category. Then came the V-1 flying bombs. German engineers, unable to develop proximity fuses for their own weapons, had nonetheless created terror weapons that pushed British defenses to the breaking point. The V-1, essentially a small, fast, unmanned aircraft carrying a ton of explosives, was nearly impossible to intercept. Too small for reliable radar tracking, too fast for manual gun laying, too unpredictable for calculated interception. On June 12, 1944, Winston Churchill personally authorized the use of proximity fuses for the defense of London. The restriction on land use was lifted, but only for this specific application. The V-1s approached over the English Channel, and most British anti-aircraft positions were along the coast. Dud shells would fall into the sea, maintaining security. The results were immediate and spectacular. In the first week, anti-aircraft batteries destroyed 17% of incoming V-1s. By the 4th week, the rate had climbed to 79%. On one remarkable day, 82% of the flying bombs launched toward London were destroyed before reaching their targets. The proximity fuse, combined with radar tracking and improved fire control, had transformed an almost indefensible weapon into target practice. German intelligence, analyzing the sudden collapse of V-1 effectiveness, couldn't explain it. British anti-aircraft accuracy had improved impossibly fast. Some analysts suggested new radar systems. Others proposed better training. No one suggested that the shells themselves had become intelligent. The secret would hold for 6 more months, until a desperate German offensive in the Ardennes would force American commanders to make the same choice Churchill had made: accept the risk of technology transfer, or accept defeat. And in bunkers and command posts across Germany, captured soldiers would begin telling stories that their intelligence officers couldn't believe. Stories about American artillery that could see in the dark, that could reach into foxholes, that exploded with uncanny precision exactly where it would do the most damage. Stories about shells that thought. The physicists at Johns Hopkins Applied Physics Lab, working 16-hour days in facilities that had been a used car dealership 3 years earlier, had taken a problem that everyone agreed was unsolvable and solved it. They had miniaturized radios to impossible dimensions, hardened delicate electronics to survive impossible forces, and manufactured them in impossible quantities. They had proven that in modern warfare, impossible was just another engineering challenge. And they had created the weapon that would make General George Patton declare, "The funny Fuze won the Battle of the Bulge for us. I think that when all armies get this shell, we will have to devise some new method of warfare. I am glad you all thought of it first." Major Friedrich Holtzmann studied the Sauer River through his binoculars as Christmas Day 1944 faded into twilight. The water was barely 40 meters wide at this point, shallow enough that his men could wade across in darkness. Behind him, the 2nd Battalion of the 914th Grenadier Regiment waited in the tree line. 426 men who had survived the first 9 days of the Ardennes offensive with their unit relatively intact. "The Americans pulled back yesterday," his adjutant, Hauptmann Werner Steiner, reported. "Our reconnaissance saw them abandoning their positions on the far bank. The crossing should be unopposed." Holtzmann lowered his binoculars. "Should be" were the 2 most dangerous words in warfare, but the intelligence appeared solid. American forces were consolidating to the north, reinforcing their lines around Bastogne. This stretch of the Sauer was a secondary objective, important mainly because it provided a potential supply route for German forces pushing deeper into Belgium. The plan was straightforward: cross under cover of darkness, establish a bridgehead on the far bank, and secure the crossroads 2 kilometers beyond. By dawn, engineers would have a pontoon bridge in place and armor could follow. It was the kind of operation Holtzmann had executed dozens of times in Russia: quick, surgical, taking advantage of enemy weakness. "We move at 2200 hours, he told Steiner. "First company leads, followed by heavy weapons. Tell the men to keep noise discipline. No smoking, no talking above a whisper. The Americans may have pulled back their infantry, but their artillery has excellent night observation." What Holtzmann didn't know, couldn't have known, was that American forward observers had indeed spotted the German concentration. And 3 kilometers behind the American lines, the batteries of the 155th Field Artillery Battalion were already plotting firing solutions. Captain James Morgan stood in the Fire Direction Center, a canvas tent heated by a portable stove, studying the map coordinates his observers had radioed. "We've got what looks like a battalion-strength formation, preparing to cross the Sauer at grid reference." He rattled off numbers while his plotting team worked with mechanical precision. "Range to target?" asked Major Thomas Bradley, the battalion commander. 14,000 yards, sir. Well within range for our 155s. Bradley nodded slowly. In his hand was a message he'd received that afternoon from Course Artillery. It was brief, almost casual in its wording, but it represented the most significant change in American artillery doctrine since the war began. The restriction on using posit fuses over land had been lifted. Every howitzer in Third Army now had authorization to fire the proximity-fused shells that had been stockpiled for months, waiting for this moment. "Load pose it for effect," Bradley said quietly. "I want every gun in the battalion ready to fire. Time on target concentration. All rounds to arrive simultaneously." Morgan felt his pulse quicken. He'd been briefed on the new fuses, had seen the demonstration footage, but the physics still seemed like science fiction. Shells that could sense their targets and detonate at optimal height automatically. No more calculating fuse settings for airburst. No more hoping that time and distance calculations were accurate. The shells would know when they were 70 feet above the ground and detonate themselves. "Sir, if I may," Morgan hesitated. "The intelligence assessment says these are veteran troops, Eastern Front survivors. If we catch them in the open with pose-it rounds, then they'll learn what the Luftwaffe learned over London," Bradley finished. "That the war has changed. Execute the fire mission, Captain." At 2147 hours, Holtzman's battalion began their approach to the river. The night was cold but clear, moonlight reflecting off the water's surface. Perfect conditions for a night crossing. Good visibility for the men, but dark enough to hide from casual observation. Lieutenant Klaus Becker led 1st Company down the slope toward the water. His 53 men moved in practiced silence, weapons held high to keep them dry during the crossing. Becker had crossed rivers under fire in Russia, had led assaults across the Dnieper under artillery bombardment. This quiet approach, with no opposition visible, felt almost like a training exercise. "First squad, into the water," he whispered. "Establish security on the far bank. Second squad follows in 30 seconds. The lead squad, commanded by Feldwebel Anton Weiss, waded into the Sauer. The water was shockingly cold, reaching waist-high at the deepest point. Weiss kept his eyes on the far bank, watching for muzzle flashes, listening for the distinctive sound of American M1 rifles. Nothing. Just the quiet gurgle of water and the labored breathing of men crossing in winter darkness. Behind them, the rest of the battalion was descending toward the river in staggered waves. Holtzman had positioned himself with the 3rd Company in the center of the formation, where he could maintain control. Steiner was coordinating the heavy weapons teams, machine gun crews and mortarmen who would provide fire support once the far bank was secured. "Looking good so far," Steiner whispered. "1st Company is halfway across." Holtzman grunted acknowledgement. Too good. The Americans didn't abandon positions without reason, and their artillery was notorious for having excellent night observation capabilities. His instincts, honed through 3 years of combat, were screaming that something was wrong. 3 kilometers away, Captain Morgan synchronized his watch with the gun battery commanders. "Fire mission, battalion pose-it concentration, grid reference." He repeated the coordinates 3 times while each battery calculated their firing solutions independently. Time on target was an American innovation that German artillery officers still struggled to believe possible. Instead of batteries firing sequentially, creating a rolling barrage, all guns fired at calculated intervals so that every shell arrived at the target simultaneously. The first battery, farthest from the target, fired first. The closest battery fired last, and for one terrible instant, an entire battalion's worth of artillery shells arrived together, creating devastation that exceeded the sum of individual explosions. With proximity fuses, the effect would be catastrophic. "Battery A ready. Battery B ready. Battery C ready." Morgan took a breath. "Execute fire mission." The 155mm howitzers spoke in carefully timed sequence, their muzzle flashes lighting up the night. 24 guns, each firing 3 rounds in rapid succession. 72 shells arcing through the darkness, their trajectories calculated with mechanical precision. Each shell carried a proximity fuse that would transmit radio waves, measure the distance to the ground, and detonate at exactly 70 feet altitude. Weiss and his squad were 30 meters from the far bank when the first shell exploded. Not near them, above them. The sound was wrong. Artillery shells landed with a heavy crump as they impacted Earth. This exploded with a sharp, vicious crack directly overhead, as if the sky itself had torn open. The shrapnel sphere expanded at supersonic velocity. 3,000 square feet of lethal metal fragments, each piece traveling fast enough to tear through flesh, bone, and steel. Weiss died instantly, along with his entire squad. The men didn't have time to understand what had happened. One moment they were wading through cold water. The next they were dead. On the near bank, Becker saw the explosion, and his mind tried to process it. Airburst. But how? The Americans couldn't see them to adjust fire, and achieving airburst precision in darkness without observation was impossible. Some lucky shell, perhaps, with a perfectly timed fuse. Then 71 more shells exploded. The detonations came so close together, they seemed like a single massive explosion. A rolling thunder that turned night into day and the air itself into flying metal. Every shell burst at precisely 70 feet, creating overlapping spheres of destruction that covered the entire river crossing. Men in the water died where they stood. Men on the near bank, thinking themselves safe from artillery that hadn't yet landed, died as shrapnel tore down through the air. Men in foxholes, men behind rocks, men in the tree line. The proximity fuses found them all. Becker, by pure chance standing in a slight depression that placed him just below the lethal radius of the nearest burst, felt the air crack above his head and was slammed to the ground by overpressure. His eardrums burst, his lungs felt crushed. When he could see again through tears and blood, the scene before him looked like something from medieval paintings of hell. The water was full of bodies, the near bank was carpeted with dead, and worst of all, men were still alive, screaming, their cries audible even through the ringing in Becker's ears. Holtzman had been 40 meters back in the tree line when the barrage hit. He'd been spared by distance, but the mathematics of what he'd witnessed were already writing themselves in his mind. 70 shells arriving simultaneously, all airburst, all at optimal height. This wasn't random luck or exceptional American gunnery. This was something new. "Get the wounded under cover," he screamed, his voice sounding muffled in his own damaged ears. "Medical teams forward. Everyone else fall back to the assembly area." Steiner was alive, barely. A piece of shrapnel had torn through his left arm, and he was trying to apply a field dressing with one hand. "Herr Major, I don't understand. How did they achieve airburst?" "I don't know," Holtzman said, and the admission terrified him more than the casualties. In 3 years of war, he'd always understood what was killing his men. Russian artillery, American bombing, partisan ambushes, all made sense within the framework of tactics and weapons he knew. But shells that exploded at precise heights in absolute darkness, without observation, without visible means of ranging or adjustment, that violated every principle of artillery he'd learned at officer school. The American guns fired again at 20:03 hours. This time, the shells landed on the assembly area where Holtzman was trying to organize his shattered battalion. Again, every shell burst at 70 feet. Again, men who thought themselves safe in covered positions died as shrapnel rained down from above. Obergefreiter Martin Kessler, huddled in a foxhole that should have protected him from anything short of a direct hit, felt the world explode above his head. The foxhole became a grave as metal fragments tore down through 3 feet of dirt and timber cover. His squadmate, Gefreiter Paul Richter, was cut nearly in half. Kessler himself took shrapnel in both legs and his left shoulder. "They can see us!" someone screamed. "They must have night observation. They're adjusting fire onto our exact positions." But that made no sense either. Adjusting fire required spotting fall of shot, correcting, firing again. These concentrations were arriving with first-round precision. It was as if the Americans knew exactly where every German soldier was standing and could kill them through any cover short of solid concrete. By 30 hours, Holtzmann's battalion had ceased to exist as a fighting force. Of 426 men who had moved toward the river, 113 were dead. 217 were wounded. The remaining 96 were either in shock or actively refusing to move from whatever cover they'd found. "Sir, we need to pull back to the defensive line," a staff officer urged. "We're in range of their artillery here. We need to get out of the kill zone." Holtzmann looked at the young officer, barely 20 years old, probably fresh from training, and saw incomprehension in his eyes. The staff officer didn't understand that there was no out of the kill zone. If the Americans could hit a river crossing in darkness with this precision, they could hit anything. Foxholes meant nothing. Trenches meant nothing. The entire defensive doctrine the Wehrmacht had developed over 5 years of war had just been rendered obsolete. "Gather the battalion commanders," Holtzmann said quietly. "Those who are still alive. We need to report this to division." The report that went up the chain of command that night was marked urgent and flagged for immediate attention by intelligence. A German major, normally stoic and professional, had used language that suggested shell shock or breakdown. He claimed American artillery had achieved sustained airburst fire without observation, that every shell had detonated at optimal height, that casualties were catastrophic despite good cover. The intelligence officer who read the report initially dismissed it as battle stress. Then he received 3 more reports from other sectors, all describing the same phenomenon. American artillery achieving impossible accuracy. Shells that exploded overhead without landing first. Casualties among troops in foxholes and covered positions that exceeded anything seen from conventional artillery. At Wehrmacht High Command, the reports landed on the desk of Oberst Heinrich Weber, Chief of Artillery Intelligence. Weber had spent 30 years studying artillery, had written the manual on counter-battery fire, and was considered one of Germany's foremost experts on indirect fire weapons. He read the reports from the Sauer River crossing 3 times. Then he reached for his telephone and called his counterpart in technical intelligence. "We need to find an unexploded American shell," he said. "I don't care what it takes. Offer rewards to frontline troops, 10,000 Reichsmarks for an intact fuse. Whatever these shells have, it's not a conventional time-setting mechanism. And if we don't understand what we're facing..." He didn't finish the sentence. He didn't need to. Back at the Sauer River, as medics worked through the night to evacuate the wounded, Lieutenant Klaus Becker sat with his back against a tree, staring at nothing. He was the only officer from 1st Company still alive. His ears were still ringing from the overpressure. His uniform was spattered with blood that wasn't his own. A medic approached him. "Sir, are you wounded? Do you need treatment?" Becker shook his head slowly. "How many?" "From 1st Company? Maybe 10 still walking. Everyone else is dead or down." 53 men. He'd led 53 men toward that river. 10 survivors. Mathematics of devastation that made no tactical sense. If the Americans had that kind of firepower available, why had they ever retreated? Why had the Ardennes offensive achieved any success at all? They were waiting for us, Becker said, more to himself than the medic. They let us come, let us bunch up at the crossing, and then, whatever they used, it was new. It was something we've never seen before. 3 days later, the whispers started spreading through German lines. Don't move during American artillery fire. Don't leave your bunker when shells are falling, even when you think they've passed over. The Americans had developed something that made foxholes and trenches death traps instead of protection. The minor mutiny that Allied intelligence would later report, German soldiers refusing orders to move during artillery bombardment, began at the Sauer River. Holtzmann's battalion, or what remained of it, was pulled from the line and reconstituted with replacements. The survivors told stories that their new comrades didn't believe until they experienced American artillery themselves. Stories about shells that thought. About artillery that could see in the dark. About weapons that made cover meaningless and turned defensive positions into killing grounds. And somewhere in the midst of those stories, the truth was getting lost. The survivors didn't know about proximity fuses, about radio waves bouncing off the ground, about vacuum tubes small enough to fit in shell noses. They knew only that American artillery had suddenly, impossibly, become deadly beyond anything they'd experienced in 3 years of war. Captain James Morgan, reviewing the after-action reports from the Sauer River fire mission, saw the numbers and felt a strange mix of professional satisfaction and deep unease. 702 enemy casualties confirmed by aerial observation, an entire battalion destroyed in less than 15 minutes of firing. The new fuses work as advertised, Major Bradley said, reading over his shoulder. Better than advertised, actually. We've revolutionized artillery warfare. Morgan nodded, but his mind was on the German soldiers who'd been caught in that crossing. Professional soldiers doing their jobs, following orders, trying to take an objective. And they'd walked into a killing ground created by physics they didn't know existed, deployed by a technology their side had declared impossible. Sir, do you think the Germans will figure it out? Develop countermeasures? Bradley shook his head. Intelligence says they tried for 10 years and gave up. Hitler himself canceled their program in 1940. Even if they captured an intact fuse tomorrow, they'd need months to understand it and years to produce copies. The war will be over long before they could deploy anything similar. Which meant every German soldier would face the same choice Holtzmann's battalion had faced. Stand and fight in positions that offered no protection, or refuse orders and face court-martial for cowardice. Some choice. The sun was rising over the Sauer River when the last of the German wounded were evacuated. The dead would lie where they fell for another 2 days before American forces advanced far enough to bury them. Major Friedrich Holtzmann, evacuated with severe shrapnel wounds, would survive the war. In 1951, during an interview with American military historians, he would be asked about the Battle of the Bulge. The moment I knew we'd lost one, he said, was Christmas night at the Sauer River. When those shells started exploding overhead, when I realized the Americans could kill us anywhere, through any cover, in complete darkness. That's when I understood. Whatever they'd invented, it wasn't just better artillery. It was a different kind of war. And we were still fighting the old one. The V-1 flying bombs came in low over the English Channel, small cruciform shapes traveling at 400 miles per hour. Unteroffizier Klaus Brenner, stationed at a launch site near Calais, watched through binoculars as another Vergeltungswaffe, vengeance weapon, roared into the sky on its tail of flame and headed toward London. "That's number 47 today," his commander, Hauptmann Ernst Vogel, noted with satisfaction. "The British can't stop them all. Even if they intercept half, the rest will reach London and deliver the Führer's vengeance." Brenner nodded, though privately he wondered if vengeance was worth the resources being poured into the V-1 Purm. Each flying bomb cost roughly what 4 fighter aircraft would cost, and the fighters could be reused. But those weren't questions a non-commissioned officer asked aloud. What neither Brenner nor Vogel knew was that 46 of those 47 V-1s would be destroyed before reaching their targets. And on one remarkable June afternoon, 82% of the V-1s launched from all sites would be shot down by British anti-aircraft guns that had suddenly, inexplicably, become terrifyingly accurate. Wing Commander David Harrison stood in the plotting room of RAF Fighter Command, watching the V-1 tracks appear on the board. Each marker represented a flying bomb detected by radar, classified by speed and trajectory. In previous weeks, destroying these weapons had been a desperate gamble. Fighters could catch them if positioned perfectly, but the V-1's speed made interception difficult. Anti-aircraft guns fired thousands of rounds with minimal success. Hitting a small, fast-moving target with timed fuses required impossible precision. Then, the Americans had shared their secret weapon. "Guns engaging now," the Air Defense Controller announced. Along the coastal belt, 3.7-inch and 90mm anti-aircraft guns opened fire with shells equipped with proximity fuses. The effect was immediate and dramatic. V-1s began exploding in mid-air with a regularity that seemed almost mechanical. Track 43 destroyed. Track 45 destroyed. Track 48 destroyed. Harrison watched the reports flow in and felt something close to relief. For weeks, London had been under bombardment from weapons that seemed almost unstoppable. Now, in the span of days, the equation had reversed. The hunters had become the hunted. At the coastal gun batteries, crews were experiencing combat that felt more like target practice. Sergeant William Thompson, commanding a gun in the Dover defenses, had fired anti-aircraft weapons for 2 years with limited success. Hitting aircraft required leading the target, calculating deflection, setting time fuses based on estimated range and altitude. A skilled crew might achieve 1 hit in 100 rounds. With proximity fuses, Thompson's gun was achieving 1 hit every 6 rounds. Target bearing 270. Range 6,000 yards. Tracking inbound, his radar operator called. Thompson laid the gun, not bothering with the complex mathematics of conventional engagement. Point in the general direction. Let the fuses do the rest. The gun fired. 4 seconds later, the V-1 exploded in a brilliant flash visible from miles away. "That's 17 today," his loader said with something approaching awe. 17 out of 19 engaged. "Sir, what are we shooting?" Thompson had been briefed to say nothing about the fuses. "American ammunition, new type. That's all you need to know." But the crew knew something had changed. They'd gone from feeling helpless against the V-1 onslaught to feeling like they were operating a system that couldn't miss. The psychological transformation was as significant as the technical one. In Germany, intelligence officers were receiving reports that made no tactical sense. V-1 loss rates had tripled, then quintupled, then reached levels that suggested fundamental British air defense improvements. Yet reconnaissance showed no new gun emplacements, No massive increase in fighter patrols. No obvious changes in defensive layout. They've improved their radar, one analyst suggested. Better tracking means better fire control. But that didn't explain how British guns were achieving airburst hits against targets moving at 400 miles per hour. The mathematics simply didn't work. Even with perfect radar tracking, timed fuses couldn't provide the accuracy needed for consistent V1 kills. Major Karl Schneider, technical intelligence officer at Luftwaffe headquarters, requested all available data on British anti-aircraft effectiveness. The graphs told a story that seemed impossible. In April, before the V1 campaign began, British coastal guns achieved roughly 3% success against high-speed targets. By late June, the rate had climbed to 74%. On June 28th, it reached 82%. This is not improved training, Schneider told his superior. This is not better radar. This is a fundamental change in weapons technology. The British, or the Americans, have developed something that makes conventional anti-aircraft fire obsolete. And I believe it's the same technology the Wehrmacht is reporting from the Ardennes. 7,000 miles away, the proximity fuse was proving equally devastating against a different enemy. Lieutenant Commander John Harper stood on the bridge of the destroyer USS Laffey, watching Japanese aircraft approach through the afternoon sky off Okinawa. The kamikazes came in groups, diving from different altitudes, coordinated attacks designed to overwhelm American air defenses. All batteries, commence firing. VT fuses authorized. Laffey's 5-inch guns opened up, joined by the 40mm and 20mm close-in weapons. The 5-inch shells, equipped with proximity fuses, began exploding among the attacking aircraft with precision that seemed almost prescient. Aircraft diving at the ship ran headlong into expanding spheres of shrapnel. Some exploded outright. Others veered off, smoking, damaged enough to lose control. Petty Officer James Wilson, manning one of the 5-inch gun mounts, watched in fascination as shell after shell burst near its target. "They're getting close," his gun captain warned, but Wilson could see the mathematics working in their favor. Every burst damaged or destroyed. No wasted shots. No shells exploding harmlessly after missing their targets. A zero dove almost vertically toward the ship, the pilot clearly visible in his cockpit. 3 5-inch rounds exploded within 50 feet of the aircraft. The Zero disintegrated, pieces of airframe tumbling separately into the sea 200 yards from Laffey. When the attack ended 15 minutes later, Harper reviewed the results with his gunnery officer. 22 Japanese aircraft destroyed. 17 by 5-inch proximity fused fire. 4 by 40mm. 1 by 20mm at point-blank range as it attempted to crash into the ship. Normal engagement. We'd have been lucky to get 5, the gunnery officer said quietly. And we'd probably have taken at least 1 hit. Sir, these fuses they're not fair. Harper laughed despite himself. War isn't fair, that's the point. But he understood what the officer meant. The proximity fuse transformed anti-aircraft fire from probability to near certainty. Aircraft approaching American ships weren't facing random fire anymore. They were facing a defensive bubble where every shell was a potential kill. Japanese pilots, briefing after missions, those who survived, reported that American anti-aircraft fire had become impossibly accurate. Shells that seemed to track aircraft, that exploded at optimal range without apparent regard for evasive maneuvers. Some pilots suggested that Americans had developed proximity-triggered weapons, but without examples to study, Japanese engineers dismissed the idea as enemy propaganda. The truth was simpler and more devastating. American industry had produced over 22 million proximity fuses by war's end. Every cruiser, every destroyer, every anti-aircraft battery had access to ammunition that increased lethality by factors of 3 to 10, and the enemy had no counter. Back in Europe, German forces were learning to fear American artillery in ways that previous generations had never experienced. Lieutenant Werner Koch, commanding a panzer crew during the fighting around the Remagen bridgehead in March 1945, discovered that American artillery could find him even when he was hidden behind hills. His Panther tank was positioned in a reverse slope defense, hull down behind a ridge that should have provided complete protection from direct fire. American forward observers couldn't see him. American tank destroyers couldn't hit him. But American artillery, firing proximity-fused shells calibrated for airburst 30 feet above ground, could kill him anyway. The first salvo exploded overhead. Shrapnel tore through the thin top armor of the Panther's engine deck. The second salvo caught Koch's crew as they abandoned the burning tank, killing 2 and wounding Koch himself with fragments that tore through his left leg. "They can fire over hills now," Koch told interrogators after his capture. "Reverse slope positions mean nothing. They don't need to see us. Their shells explode in the air and rain shrapnel down. There's no defense except staying buttoned up inside armor, and even that only works if you never open a hatch." The psychological impact was spreading faster than the technology itself. German infantry who had never encountered proximity fuses heard stories from units that had. The stories grew with retelling, becoming almost supernatural. American artillery that never missed. Shells that could sense soldiers hiding in buildings. Weapons that made foxholes into graves. Feldwebel Anton Schmidt, a veteran of 4 years on the Eastern Front, experienced his first proximity-fused barrage during the fighting in the Hürtgen forest. His squad was dug into well-constructed bunkers, overhead cover reinforced with logs and earth. By conventional standards, they were safe from anything short of direct hits. The American barrage lasted 3 minutes. Every shell exploded at precise height. Shrapnel tore through overhead cover that should have been proof against fragments. Of Schmidt's 12-man squad, 9 were casualties. Schmidt himself survived because he'd been in the deepest part of the bunker, below ground level, when the barrage hit. "I've been shelled by Russian artillery for 3 years, he said afterward, his hands still shaking. "I thought I understood what artillery could do. This was different. This was intelligent. Every shell knew exactly where to burst. There was no safe position except deep underground." The stories reached units that hadn't yet faced the new weapons, creating anticipatory dread. Orders to advance became death sentences in soldiers' minds. Staying in defensive positions meant being targeted by artillery that could kill through any cover. Advancing meant moving through open ground, where proximity-fused shells would find you. Some units began refusing orders, not from cowardice but from rational calculation that obedience meant certain death. The minor mutinies that Allied intelligence reported weren't organized resistance. They were the spontaneous breakdown of soldiers who understood that the rules of war had changed and they hadn't been issued the new rulebook. German efforts to capture intact fuses became desperate. Rewards were offered. 10,000 Reichsmarks, enough to buy a house for anyone who recovered an unexploded shell with fuse intact. Forward units were ordered to search for duds, to collect fragments, to document anything unusual about American ammunition. When examples were finally recovered and sent to technical intelligence, the results were worse than ignorance. German engineers examined the fuses and declared them impossible. The vacuum tubes couldn't survive the acceleration of firing. The battery couldn't function reliably. The entire design violated principles of what could be manufactured in wartime conditions. "This is propaganda," one engineer wrote in his report. "A shell constructed to convince us that Americans possess technology they could not possibly produce in quantity. The reported effects must come from improved radar fire control, not from the shells themselves." It was easier to believe the Americans were lying than to accept that German engineering had been surpassed so completely. By April 1945, proximity fuses had become standard issue for American artillery. The 105mm howitzer, the workhorse of divisional artillery, could now fire proximity-fused shells that made every barrage an airburst barrage. The effect on German defensive doctrine was catastrophic. Tactics developed over 5 years of war: dig in, stay low, wait out the bombardment, no longer worked. Oberst Heinrich Weber, the artillery intelligence officer who had requested intact fuse specimens, finally received definitive proof in late March: an unexploded American shell, fuse intact, recovered from the Remagen area. Engineers at the weapons testing facility in Hillersleben examined it with instruments and expertise accumulated over decades. Their report, delivered to Wehrmacht High Command in early April, was brief and devastating. The device uses miniaturized vacuum tubes and radio transmission to sense ground proximity and detonate at optimal height. Manufacturing quality exceeds German capabilities. Production in quantity would require industrial capacity we do not possess. No countermeasure is possible except remaining underground. Recommend immediate development of German proximity fuse program. The recommendation came 5 years too late. Hitler had cancelled German proximity fuse development in 1940, declaring it impossible to complete within 6 months, and therefore not worth pursuing. The engineers who had been working on the problem had been reassigned. The research facilities had been converted to other projects. And now, in April 1945, with Germany collapsing on all fronts, there was neither time nor resources to restart what had been abandoned. Weber read the report in his office, then carefully filed it away. There was no point sending it higher. The High Command had more immediate concerns than technological inferiority. The war would be over before any German proximity fuse could be developed, tested, and produced. But Weber kept a copy for himself. After the war, he would show it to American interrogators and ask the question that haunted him: "How did you solve the vacuum tube problem? Our engineers said it was impossible." The Americans would smile and answer, "We stopped trying to make the impossible work. We invented something new that was possible." In the Pacific, Japanese engineers were reaching similar conclusions. Captured proximity fuses from downed American shells revealed technology that seemed decades advanced. The miniaturization, the ruggedness, the sophistication of the circuits all exceeded Japanese capabilities. Commander Takashi Yamamoto, technical intelligence officer with the Imperial Japanese Navy, examined examples recovered from Okinawa and wrote a report that never reached higher command before the surrender. American proximity fuses represent fundamental industrial superiority. They have miniaturized complex electronics, hardened them for artillery use, and produced them in quantities that suggest unlimited manufacturing capacity. Japan cannot duplicate this technology with current resources. Recommend acceptance that American technological advantage is insurmountable. The report was dated August 1st, 1945. 14 days later, Japan surrendered. The proximity fuse hadn't won the war alone, but it had fundamentally altered the mathematics of combat, turning near misses into kills, making defensive positions death traps, and proving that in modern warfare, Technology could multiply force more effectively than numbers or courage. And it had done something perhaps more significant. It had demonstrated that the impossible was just another engineering problem, waiting for someone stubborn enough to solve it. The production statistics, examined coldly, tell a story of industrial dominance that borders on the absurd. 22 million proximity fuses manufactured between 1942 and 1945, each one containing 130 separate components, each one assembled by hand, tested individually, calibrated to function within tolerances measured in microseconds. At peak production, American factories were completing 70,000 fuses daily, one every 1.2 seconds, around the clock, 7 days a week. The cost had been staggering. Over $1 billion in 1940s currency, equivalent to $15 billion today. More than the Manhattan Project spent on the atomic bomb. But unlike the atomic weapon, which was used twice, proximity fuses saw combat in every theater, on every front, in circumstances ranging from anti-aircraft defense to ground combat to naval bombardment. And they had fundamentally rewritten the rules of warfare. Dr. Merle Tuva, the physicist who had led Section T through 4 years of impossible challenges, stood in the Applied Physics Laboratory in September 1945 and tried to calculate what his team had accomplished. The numbers were almost meaningless in their scale. Based on pre-war anti-aircraft effectiveness rates, destroying the number of aircraft that proximity fuses had accounted for would have required roughly 300 million conventional shells. The fuses had saved ammunition, saved lives, and most significantly, had made air defense actually work. "We invented a weapon that made other weapons obsolete," Tuve told a reporter, who'd been cleared to write about the project now that the war had ended. "Not just German weapons or Japanese weapons. Our own weapons. Every anti-aircraft gun, every artillery piece, every defensive doctrine based on the assumption that shells land before they explode. All of it became outdated the moment these fuses entered service." Dr. James Van Allen, whose vacuum tubes had solved the impossible problem of surviving artillery acceleration, was more direct in his assessment. "We created something that shouldn't have been possible, proved it worked, and then manufactured it in quantities that made it normal. That's the American approach to warfare. Make the impossible routine." The post-war testimonies from German and Japanese personnel revealed the psychological impact more clearly than any combat report. In 1947, Allied intelligence officers conducted extensive interviews with former enemy soldiers, seeking to understand how they had perceived American technological superiority. Major Friedrich Holtzmann, recovered from his wounds sustained at the Sauer River, sat across from an American captain in a POW camp and tried to explain what it had been like facing weapons that violated every principle of artillery warfare he'd learned. "The mathematics were impossible," Holtzmann said, speaking slowly as his words were translated and recorded. "I commanded artillery before the war. I understood trajectory, timing, fuse settings. What your shells did at the Sauer River couldn't be achieved with conventional fuses. We thought perhaps you had perfect observation, radar that could track individual soldiers. But that still wouldn't explain the precision. Every shell burst at optimal height. Every one. That's not observation. That's something in the shell itself." The interviewer nodded. "We can show you a proximity fuse now. The war is over. Would you like to see one?" Holtzmann examined the device for several minutes, turning it carefully in his hands. The miniaturization impressed him. The ruggedness amazed him. But what truly stunned him was learning that over 20 million had been produced. "We tried to develop this," he said quietly. In the 1930s, our engineers worked on proximity fuses. They concluded it was impossible. Too many technical problems, too complex for mass production. Hitler canceled the program in 1940. And you made 22 million of them? The first cost $700 each, the captain explained. By the end, we were making them for $18. Volume manufacturing, interchangeable parts, assembly line production. Once we solved the technical problems, the rest was just industrial capacity. Holtzman set the fuse down carefully. That's what we never understood. We assumed our technical problems were everyone's technical problems. If German engineers declared something impossible, we believed it was impossible. You assumed that impossible just meant difficult, and difficult could be solved with enough effort and resources. Similar conversations were happening in interrogation centers across occupied Germany and Japan. Former Luftwaffe pilots explained how American anti-aircraft fire had transformed from a minor nuisance into an impenetrable barrier. Japanese naval officers described watching kamikazes disintegrate before reaching their targets, destroyed by shells that seemed to track aircraft actively. Commander Takashi Yamamoto, the Japanese technical intelligence officer whose report had never reached high command, was particularly eloquent in his post-war interview. When we examined captured American fuses, we understood that Japan had lost before the first shot was fired. Not lost the war, we knew we would probably lose eventually, but lost the technological competition. You had miniaturized electronics, hardened vacuum tubes, mass production of complex components. We were still struggling with reliable radio sets for aircraft. The gap wasn't years, it was decades. The German engineers who had examined captured fuses and declared them propaganda were more subdued in their post-war assessments. Oberst Heinrich Weber, who had requested those examinations, admitted in a 1948 interview that he had simply refused to believe what the evidence showed. The fuses we examined were genuine, he said. Our engineers were correct that they represented manufacturing capability beyond German industry. But instead of accepting that America had surpassed us, we convinced ourselves it must be deception. The alternative, that we were fundamentally outmatched, was too psychologically devastating to accept. The proximity fuse's impact extended beyond the immediate combat effects. It had forced a complete revision of military doctrine. General George S. Patton's statement that the funny fuse required a new method of warfare proved prophetic. Post-war military planning incorporated the assumption that proximity-fused weapons would be standard equipment, fundamentally changing how armies approached offensive and defensive operations. Foxholes, which had protected infantry since World War I, were now inadequate against airburst munitions. Overhead cover needed to be significantly stronger. Defensive positions required actual bunkers, not just holes in the ground. The entire concept of how infantry survived on the battlefield was rewritten. Anti-aircraft doctrine changed even more radically. Pre-war planning assumed that defending cities required thousands of guns firing millions of rounds. Post-war planning showed that a fraction of that force, equipped with proximity fuses, could provide better protection. The efficiency increase made air defense actually viable, which in turn forced changes in how aircraft were designed and deployed. The Soviet Union, which had received proximity fuse technology from the United States during the war, immediately began copying and improving the design. By 1950, Soviet-produced proximity fuses were appearing in weapons systems across the Eastern Bloc. Technology became standard worldwide, spreading from American innovation to global standard in less than a decade. But the most significant legacy was psychological. The proximity fuse proved that technological superiority could multiply combat effectiveness more efficiently than numerical superiority. A smaller force with better technology could defeat a larger force with conventional weapons. This lesson would shape military development for the rest of the century. On a cold morning in December 1965, 21 years after the Battle of the Bulge, a reunion was held at Fort Sill, Oklahoma. American artillery officers who had served in World War II met with their German counterparts, now allies in NATO, to discuss the evolution of artillery doctrine. Colonel George Axelson, retired, stood at a podium and recounted his decision to use proximity fuses at Monschau on December 16, 1944. He had violated Eisenhower's direct orders. He had risked court-martial. He had authorized the use of America's most closely guarded secret because American soldiers were dying, and he had the weapon to save them. "I made the decision in about 3 seconds," Axelson told the assembled officers. "Training says you never violate orders from Supreme Commander. But training also says you do whatever it takes to protect your troops. So I chose my men over my orders, and I expected to face consequences." He smiled slightly. Instead, within 48 hours, Eisenhower himself lifted the restriction. The Pentagon had wanted to protect the technology. Eisenhower wanted to win the war. The fuses proved so effective that keeping them secret became less important than using them. And once we started using them over land, the war changed. In the audience, Friedrich Holtzmann, now Brigadier General Holtzmann of the Bundeswehr, listened with the perspective of someone who had experienced both sides of that technology. After the presentation, he approached Axelson. "I was at the Sauer River," Holtzmann said through a translator. "Christmas night, 1944. My battalion was attempting a crossing when your artillery found us. I lost over 400 men in 15 minutes. Axelson's face fell. "I'm sorry." "Don't be," Holtzmann said. "We were at war. You were defending your positions with the best weapons available. But I've spent 20 years trying to understand what happened that night. How your artillery achieved such precision in darkness. The fuses explain it. And they explain why Germany lost. Superior firepower? Superior willingness to solve impossible problems," Holtzmann corrected. "We declared proximity fuses impossible and gave up. You declared them difficult and kept working. That difference in attitude decided the war more than any battle." The two officers shook hands, former enemies united by recognition that technology had transformed warfare in ways neither side had fully anticipated. Back in Monschau, where Axelson had made his decision that December morning, a small monument now stood near the old command post. The inscription was simple. Here Colonel George Axelson authorized first combat use of proximity fuses over land, December 16, 1944. This decision saved countless Allied lives and demonstrated American technological superiority. What the monument didn't say, but every artillery officer understood, was that Axelson had done more than save lives that morning. He had proven that technological innovation, properly deployed, could alter the course of war. That weapons which seemed like science fiction could become standard equipment. That the impossible was just a temporary description for things that hadn't been invented yet. The Germans who had laughed at American industrial capacity, who had dismissed reports of revolutionary weapons as propaganda, who had declared proximity fuses physically impossible, had learned the hardest lesson of modern warfare. In the contest between those who believe in limits and those who refuse to accept them, the believers in limits will always lose. Colonel Axelson made his decision in 3 seconds on a December morning in 1944. The consequences echoed through 70 years of military development, influencing every missile, every smart weapon, every precision-guided munition that followed. The proximity fuse was the first weapon that thought, the first artillery shell that could sense its environment and react appropriately. Every weapon system that followed, from heat-seeking missiles to radar-guided bombs, descended from that fundamental innovation. The funny fuse, as Patton had called it, had indeed won the Battle of the Bulge. But more significantly, it had won the technological war that underpinned the shooting war. It had proven that American industry could produce the impossible, that American scientists could solve the unsolvable, and that American manufacturing could make miracles routine. 22 million miracles, each one assembled by hand, each one capable of turning near misses into kills. The Germans had 30 to 50 different proximity fuse designs in development. None ever saw service. The Americans had one design that worked. They produced it by the millions. And in that difference lay the entire story of why the war ended the way it did. Every day, we uncover the stories behind the weapons, tactics, and technologies that won World War II. Stories that go far beyond what you learned in school. From the engineers who made the impossible routine, to the soldiers who first wielded weapons their enemies thought were science fiction, to the psychological impact of facing technology decades ahead of its time. Hit that subscribe button and ring the notification bell so you never miss an episode. Because the proximity fuse isn't the only impossible weapon that changed warfare. We're just getting started.